This is sample 9-1 on page 372. It's our only sample from this section. We'll have a whole lot more in the next section. This is going to illustrate conservation of momentum and discuss what happens to kinetic energy. So in this scenario, you have a mass of 50 kilograms and you have a skateboard of a mass 2.5 kilograms. Now this problem starts with you at rest on your skateboard. So since you are at rest and your skateboard is at rest, the total momentum of the entire system is 0 at the beginning, okay? Which means that, okay, the entire momentum at the end of this story is also going to be 0. So just keep that in mind. You push off your skateboard with a speed of 0.6 meters per second and you move to the left. So the question is, what's the skateboard speed after you push off? So your instinct should be either from experience or from the example we had in the slideshow, that the skateboard is going to be moving, number one, to the right. Okay, if he moves to the left, the skateboard is going to move to the right, and that it's going to be going quite a bit faster than you because it has quite a bit of a smaller mass. And we'll see that again and again and again. If something large collides with something small, then the effect on the smaller object is usually much greater. So that's our kind of mindset here. Let's write down some data. I'm going to use the subscript of Y for you and write down that your mass is 50 kilograms. I'm going to use the subscript S for skateboard, and I'm going to note that that is 2.5 kilograms, all right? All of the initial velocity, that is the initial velocity of you, and the initial velocity of the skateboard is all 0. Everyone's at rest. But we're told that your final velocity, the final velocity of you, is 0.600 meters per second to the left. Remember, momentum is a vector quantity, and even though your instinct might be to make left negative, and that's absolutely fine, let's make it positive just for grins, because we're given it. You can do this problem again with left being negative. You will get the same answer, I promise. The thing about momentum and collisions is that almost all the time, much of the time, the objects are going to move in opposite directions after a collision, so something's going to be negative. It doesn't matter at all which one it is. So what are we looking for? We're looking for the final velocity of the skateboard, right? So we know that our initial momentum is 0, total U plus skateboard. So our final momentum, U plus skateboard, must also be 0. But let's figure out your final momentum, the final momentum of you. And I'm probably switching the order of the subscripts, but don't worry about it. You've got I and F for initial and final, Y and S for you and skateboard, and it doesn't matter. So we've got 50 kilograms. I didn't write this down. I probably should have. The formula, P equals mv, okay? So your mass, okay, times your velocity, all right? And we are just sort of taking left to be positive. So we get 30.0 kilogram meters per second. There's that lovely unit again. Now the direction of your momentum is, I'm just gonna write L with a circle around it, to the left, okay? So since our initial total is 0 and our initial final is 0, my skateboard's momentum has to balance this out. So the final momentum of the skateboard is going to be 30 kilogram meters per second to the right. Okay, it needs to balance it out. So if you like, you can call that negative 30.0 kilogram meters per second, if you'd like. All right, so what are we looking for? We're looking for VF of the skateboard, okay? So we know that P, the final momentum of the skateboard, is equal to the mass of the skateboard times the final velocity of the skateboard. So the final velocity of the skateboard is the final momentum of the skateboard divided by the mass of the skateboard. So 30 kilogram meters per second over 2.5 kilograms. Okay, and if you want to, and we'll keep the negative in there just to be consistent. So our final velocity of the skateboard is negative 12 meters per second. And according to our scheme, where to the left is positive, then we have 12 meters per second to the right. Right? You never want to give me this answer. Okay, you don't want to say the velocity is negative 12 meters per second. That doesn't mean anything. Even if you hedge and say, oh, well, left is positive. Nope, your answer is 12 meters per second to the right. Now, in a problem that's fairly simple like this, you can sort of, and I don't even discourage you from not really worrying about the negative sign, because if in your head you understand you go left, skateboard goes right. I'd almost rather have you understand the physics of this than to blindly plug in these negative signs. But I want to also show you that the scheme that you come up with and the math does translate, and it will give you the correct answer. And things get difficult, as you saw in the Sled Wars demo or gizmo. Things don't always go the way you think they're going to go. So if there's ever any doubt, keep the negative signs and you'll get the right answers. Okay, that's part A, 12 meters per second to the right. And as we guessed, it is quite a bit faster than U, okay, because of the smaller mass. Okay, the next part of the problem talks about kinetic energy. So let's see what happened to kinetic energy. And where we're going with this is that in some collisions, kinetic energy is conserved, and we're going to call that an elastic collision. And in some collisions, momentum is not conserved, and we're going to call those inelastic collisions. Now, we're not going to get to that until the next topic, but let's just bring it up here. So this is part C. All right, the initial kinetic energy is zero, right? Because we started off at rest. Your kinetic energy after the collision is 1/2 mvu final squared, all right? Which is half times 50 kilograms times 0.6 meters per second, quantity squared, 9 joules. Right? Kinetic energy of the skateboard is 1/2 mass of the skateboard, velocity of the skateboard squared. So that's 2.5 kilograms, 12.0 meters per second. Quantity squared is 180 joules, right? There's quite a bit of difference there between the kinetic energy of you and the kinetic energy of the skateboard. And remember, when we're looking at the formula, what matters more? It's linear with mass, but it's quadratic with velocity. So even though the skateboard has a smaller mass, right, that much higher speed is going to give it a much more energy. And this is going to have a lot of ramifications in sports and firing projectiles. Why do you want to get them as small as possible so that you can give them as large as a velocity as possible? So I've droned on long enough about the first example in the book. Hopefully this helps you out.